What if everything you know about numbers, rational, irrational, even infinity, could be built from just a few simple axioms? Today, we define the axioms that provide the necessary structure for real analysis. To do this, we are looking at Chapter 1 of Walter Rudin's Principles of Mathematical Analysis, the definitive text for constructing this rigorous foundation. The entirety of calculus operates on the concepts of limits and convergence. It is how we measure instantaneous change and accumulate infinite slices of area. But to measure that convergence without running into mathematical paradoxes, the space we operate in must be perfectly continuous. It cannot have hidden holes. To guarantee that, we have to rebuild the real number system from the ground up, starting with basic axioms. Our visual intuition suggests a number line is solid, but intuition is not a mathematical proof. Without a rigorously constructed continuum, the convergence of sequences, the mechanism behind calculus, cannot be guaranteed. Example 1.1 demonstrates why the rational number system is inadequate. It tries to find a rational number p satisfying p squared equals 2. If p is a fraction m over n in lowest terms, algebra gives m squared equals 2n squared. Both m and n must be even, leading to a mathematical contradiction. Because no rational number squared equals exactly 2, we can divide the positive rational numbers into two groups. Set A contains all fractions where p squared is less than 2, and set B contains fractions where p squared is strictly greater than 2. Plotting this leaves a distinct empty space, precisely where the square root of 2 should exist. Because fractions can always be subdivided, set A contains no absolute largest number, and set B contains no absolute smallest number. They infinitely approach the void, but never bridge it. The math proves that the rational number system is riddled with structural gaps, sitting exactly where the irrational numbers belong. This lack of completeness completely prevents the system from supporting the limit operations that are required for analysis. Before we can fix these holes, we need to establish the exact architectural rules that the rational system does successfully obey. These fall into two categories: field axioms and order axioms. A field is a set of numbers with addition and multiplication that follow strict rules. Axioms for addition guarantee commutativity and associativity. They also dictate every number has an opposite counterpart. Axiom A5 ensures an additive inverse brings the sum perfectly back to 0. Next, an ordered set allows us to definitively rank elements. Definition 1.5 states that for any two numbers x and y, only one of three statements is true. X is less than y, x equals y, or y is less than x. The rational numbers form an ordered field. You can do algebra and you can rank the results, but being an ordered field is not enough to prevent the gaps we discovered in the previous scene. To seal these gaps, we must introduce a new mechanical property to our system, the concept of mathematical bounds. A set is bounded above if there is a number greater than or equal to every element inside it. You can place arbitrary upper bounds to the right of the data, but the most important bound is the supremum, the least upper bound. This smallest possible boundary locks on to its rightmost edge. In our earlier example with the square root of 2, set A had many rational upper bounds, like 1.5 or 1.42. But because there was no absolute largest rational number inside the set, a least upper bound simply did not exist within the rational system. This brings us to definition 1.10 in the text, the least upper bound property. An ordered set has this property if every non-empty subset that is bounded above has a supremum that exists within that same overarching set. Rudin then introduces theorem 1.9. This is the existence theorem declaring that there is a unique ordered field equipped with this precise least upper bound property. That field is the real number system. By strictly enforcing this rule, the empty space at the end of set A is forced to exist as a valid point on the line. The square root of 2 is formally recognized and filled. The least upper bound property ensures that the continuum is unbroken. This is the structural requirement that provides the rigorous foundation for every limit operation in analysis. Enforcing the completeness axiom determines the specific scale and density of the real field, leading to the consequences detailed in theorem 1.20. Part A establishes the Archimedean property. It states that no matter how small a real number x is, and no matter how massive a real number y is, you can always multiply x by a large enough integer to eventually surpass y. This proves there are no infinitely small or massive real numbers. The entire field is measurable. Part B defines the density of rational numbers, proving that between any two distinct real numbers, you can always find a rational number wedged exactly between them. The real field is not just gapless, it is infinitely dense and universally scalable. Even with a perfect continuum, the real field has a strict algebraic limitation. You cannot solve the equation x squared equals -1. A negative times a negative is always positive. To solve this, we construct the complex field. Instead of single points on a 1D line, we define numbers as ordered pairs of real numbers, mapping our mathematical space onto a 2D plane. This new system satisfies the field axioms we established earlier. Definition 1.24 lays out the exact operational rules for how to add and multiply these specific ordered pairs. If we define the imaginary unit I as the coordinate pair 0, 1, applying those multiplication rules mathematically proves theorem 1.28, I squared equals -1. But this expansion requires a trade-off. The complex field is not an ordered field. Because we are operating in 2 dimensions, you cannot mathematically state that one complex number is greater or less than another in a linear sequence. Mathematics requires sacrifice. We surrender the ability to rank numbers linearly in order to gain a system where every polynomial equation has a guaranteed solution. To summarize, the rational number system is a sequence of fractions with infinite gaps. The least upper bound property fills those gaps, creating the continuous real number continuum. Expanding that line into a plane creates the complex field, exchanging linear order for algebraic freedom. Without the rigorous foundational proofs provided by these axioms, the limit processes of calculus would lack the necessary mathematical certainty. If you want more deep, structured explanations from books like Rudin, don't forget to like, subscribe, and join this journey into higher mathematics.